developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
My background is in energetic materials, in solid propellants, solid fuels, and in this project we're trying to integrate solid fuels into rotating detonation engines. In solid fuels, why we're interested in that is because they're much easier to store. They don't leak. So if there's a puncture in the device, you're not going to have a fire hazard with that. Potentially it could have higher energy density. But the challenge of bringing in a solid fuel into the RDE is how do we integrate it in? How do we go from a solid fuel to a gaseous fuel that the RDE can operate with? So that's a big focus of this project, is looking at fuels that can gasify on their own. So we don't have to bring in energy to turn that fuel into gas, but they burn, they propagate, and produce gas that can be fed into the rotating detonation engine.
Some of the advantages of a rotating detonation engine include increased thermal efficiency due to the higher temperatures and pressures that occur during a detonation. In the video shown here, for example, the detonation wave is propagating at a speed of over 1,500 meters per second, which is over 3,000 miles per hour. This is up to 100 times faster than the flame in a typical engine, which leads to increased power density, so that the combustor can be made much more compact, simple, and lightweight than a normal combustor, which reduces the overall fuel consumption. So the goal of the research at Purdue University is to investigate the types of solid propellants that can be used in a rotating detonation engine, as well as the systems that would be required to incorporate those solid propellants effectively in an operating rotating detonation engine.
For this project, we're looking for solid fuel with some pretty unique characteristics. First, we wanted it to be able to self-deflagrate in a non-oxygen atmosphere, and that's pretty important for how we will get it to actually work in an RDE. We also wanted to produce very fuel-rich exhaust products, ones that are hopefully very detonable, like hydrogen gas. And ideally, this is something that we want to be able to produce in-house. That way we can kind of fine-tune the formulation or add in any type of energetic additives as well. One of the first things that we did for this project was essentially using a synthetic mixture to simulate what we think our solid fuel will produce in the RDE. So to do that, we use NASA CEA, which is Chemical Equilibrium with Applications code, in order to simulate the propellant burning. And then we were able to take that and take the constituent gases, mix them together, and fire that in an RDE. So that's something that one of my previous colleagues did. Here at Purdue, we have many RDEs that we're able to test with. Specifically, we have optically accessible ones, which is useful for us to visualize what's happening inside the RDE. And we use these in the solid fuel project to do our tests. So one of the next things that we did was use Raman spectroscopy to actually measure the products of our solid fuel. And that's just because any simulation software, especially one that's kind of first order like NASA CEA, is going to produce results that are not necessarily in line with reality. So using Raman spectroscopy, we're able to very accurately measure the concentration of all the different species inside our solid fuel exhaust products. And that kind of helps us determine if we need to tweak the formulation, as well as will give us a better understanding of how it will actually operate inside an RDE. One of the things that we wanted to do is characterize how detonable those products are. And so we use a detonation tube, which is essentially a long acrylic tube that we're able to image with high-speed cameras to actually measure how fast those exhaust products are able to detonate. And then doing that, we're able to kind of give ourselves a benchmark for how well our formulation is doing. And that kind of is an important metric to understand how we'll actually operate inside of a RDE once we get to that point. So our next steps in the near-term future is scaling up our production of this solid fuel. That's going to allow us to do larger scale tests, as well as actually integrate the solid fuel into the RDE. We're also been looking at various additives that we can add to that solid fuel formulation to produce exhaust products that are more tailored to the specific use case. Some of the experimental setups that we've been updating, we have a new Raman spectroscopy setup that's going to allow us to measure the solid fuel exhaust products in a more realistic environment. And that's going to give us a better idea of the actual formulation that we're working with inside the RDE. And then we also have a larger det tube, and that's going to kind of fix some of the issues that we first saw in the original setup and allow us to get more accurate measurements of the wave speed of our detonation.
The idea to use solid propellants for rotating detonation is a fairly new one. So some of the innovative work that's been done at Purdue and a couple other places in the US is really cutting edge technology. So we've demonstrated burning propellants and producing something that could then burn again in a rotating detonation engine. So that proof of concept is really key to being able to turn on, additional funds to do a more substantive effort in maturing this technology for an actual application. There's a lot of work been done with liquids, but rotating detonation with solid fuel is pretty new game. It's a very high interest technology across Department of Defense. So it's a very important technology for the warfighter.